What's up, guys? I hope you all are doing well. Welcome back to my YouTube channel and welcome back to another YouTube video. In this video, we will be looking at part 2 of our scientific and numeric computing tutorial series in Python. So as you know, we are looking primarily at the Scipy and the NumPy package in Python. Okay, guys, so if you have been following along as well, you'd realize that in the previous video, we spoke about the important concepts that we will analyze in this tutorial series. That being, we spoke about Python programming language in general, a small overview. We spoke about Python NumPy package as well as Scipy package. Okay, I gave you a short or brief overview of the uses and how powerful these packages really are. Then towards the end of that video, I also provided you with a short overview of how to just install NumPy and Scipy on your machine. So that's what we will be covering in this video, along with making a start to the coding itself. Now, I'd like to first mention that I have a few commands here which I sourced from Google, and it basically helps you to install the Python NumPy and Scipy packages on your machine depending on what operating system you are working with. So if you are on Windows, Linux and Mac, well, Windows is the one that I'm most familiar with, so we'll utilize pip. And what I'd like for you guys to do is pick out the one that works for you and try that. I sourced these from Google, so I hope they are right. Okay, I'm not too sure because I've never worked with Mac ports and Fedora and so on. So head over to your shell or your terminal and type pip install NumPy. Give it some time and you'll have NumPy installed on your machine. Next, I would like you to do pip install Scipy. Give that some time as well and you will have it installed on your machine. If you don't want to install them individually, you can basically queue them up for installation, and you can provide the names of the packages separated by a space character. Okay, and doing that, you'll still have the packages with you on your machine. Once that is done, we are ready to start exploring the NumPy package first. I'd like to mention you can go about practicing this tutorial series in two ways: via the interactive console, getting your output and input directly from here, or you can do it in the editor, okay, where you code the commands and you run the script. Well, I'm going to be working with the editor because my goal for this series as well is at the end of the series, I want each of us to have our own Python script in which we have a complete breakdown and sort of documented code that talks about the NumPy package and another that talks about Scipy. So basically in future when you need to revise or just brief yourself with these packages, you already have a very well formatted script that you can use to reference and teach yourself. So that's that. Now let's get to it. First things first, import NumPy as np. So in order to use the NumPy package, we need to import it, and we import using the alias np. So every time we reference a function or a method or a piece of code from the package, instead of saying numpy dot, numpy dot, we do np dot and whatever we'd like to access. So let's begin with the first comment: import package numpy as np. Moving on. The NumPy package, guys, the first function that we look at is what's called np.arange. The NumPy or np.arange function will create for us a NumPy array containing evenly spaced elements. Okay, by that I mean we have to pass a few parameters, the compulsory one being the stop parameter. By default, this function starts at 0 and the step is 1. So passing, let's say we want to generate an array that consists of maybe 10 million elements. Okay, the way in which we do that is pass the value 10 million inside here. 10 million, in case you don't know, is basically the number 1 followed by 7 zeros. That looks about right. One more. Right, 7 zeros, guys. This is our numpy.arange. So we can create an array object. ARR is equals to numpy.arange from 1 to 1 or 10 million with a step of 1. So these step and start are optional parameters. I'm providing them here so you know we have a better understanding. Start is 1, stop is 10 million, step is 1. Okay guys, so this is probably the technique that I will deploy. I will try to include the names of the parameters where I can, because upon seeing the names of the parameters, you'll get yourself very acquainted and familiar and comfortable with using the packages. Okay, so let's go ahead and print this array to the screen and we'll have a look at the output. So as we can see, right, we have a huge array, and this tells us itself now that the arange function works similar to the range function in a sense that it is exclusive of the stop number. As you can see, we only have the last value, not 10 million, it is actually 9.9 million and some digits. So that's that. Now, in the event of us working with a NumPy array, right, I would like to introduce you to a method that is called shape. And notice guys, this shape method needs to be called on a NumPy array. Okay, so let's go ahead and run this again. Array.shape, and have a look at the output guys, and notice that what we are working with here is the shape method will output to us a tuple, and in this tuple will be two values in the form of rows and columns. Okay, what I'm saying is that the first value in the tuple represents the number of rows, and the second value in the tuple is the number of columns. This tells us that we are working with one large column in which there are 9.9 million rows and some digits. Okay, so that is a function or a method that I wanted to introduce you to in an early stage. So from now onwards, any NumPy array that you create, if you don't know how many rows or columns or elements you are working with, you have the shape function or method to tell us exactly that. Okay, it will tell us the shape of the array. In this case, we are working with an array containing 9.9 million elements. Okay, and these 9.9 million elements are in the form of 9.9 million rows, each one getting its own row, and all of them are arranged in a columnar format. Okay, moving on, let's say let's comment this for you. So create an array with 10 million elements. Okay guys, so another interesting thing that I'd like to introduce us to, right? So what I will do as well is, I'm not sure if other IDE software supports this feature, but Spider allows us to create cells to basically segment our code, and that's what I will do at times. So when we run the script, we don't get shown all the output of previous code lines. Okay, so I would like to now introduce you to something that you may not know Python actually supports. This does not come from NumPy, it comes built into Python, but when you combine this syntax with NumPy itself, it really gives a whole new meaning and adds another level to scientific and numeric computing. Okay, it's a shorthand for integer values. There are several that exist, but here's one that I'd like to introduce you to now. Okay, so you guys don't have to stress, because you are probably wondering why are we working with arrays that have 10 million elements. You know, I'm a beginner in NumPy. Why can't you give me an array with 5 or 10 elements? Gradually or eventually we will do that, guys. For this specific exercise, I chose these numbers for a reason. Anyway, I would now like to create an array with 10 million elements using scientific syntax. So don't get intimidated, right, by the words scientific syntax. I'm just calling it that. Essentially, you know how we have exponential forms of integers? That's basically what it is. NumPy.arange start is equals to 1, stop is equals to, I can type 10 million again, but that's not the point. Here we have a shorthand, 1 to the exponent 7. That's the number 1 followed by 7 zeros. Okay? And that leads us to 10 million. So start, stop, and step is equals to 1. Now take a moment to distinguish between these two techniques or approaches we took, guys. You can use whichever one you are comfortable with, but all in all, in the real world of scientific and numeric computing with Python, especially those physicists and statisticians and so on, they utilize this scientific syntax. Okay, output will be exactly the same. Nothing changes except for the fact of how our numbers are represented. Okay, here we have a scientific representation of integer values, and here we have our standardized representation. Okay, so the shape itself will be the same. Okay, add a comment here as well. We can just say printing the NumPy array, and here we'll say printing the shape of the NumPy array. That's good, so no need to repeat ourselves. If you are that kind of person who is meticulous, you can copy and paste these comments so you have a well organized script. Okay, so that's two interesting stuff we've learned so far. That's provided to us by the NumPy array, and it's good to know that NumPy actually supports this shorthand of integers, because in the real world, if you are processing, SQL databases or Oracle databases, we don't deal with 5, 10, 20, 100,000 rows. We deal with millions. Okay, in some cases it goes up well into the quarter of a billion. So that's that. Anyway, let's move on. So what I'd like to demonstrate now, right? This is not something that's compulsory for you to know. You just need to be aware of the difference between a typical list and a NumPy array. Okay, the difference between those, especially when it comes to talking about the processing concept or the processing differences. Okay, so what I will create there is a list array. Oftentimes you'll hear list arrays called list arrays. Okay, so basically we'll just do array dot to list, and as you can see, Python will transform or convert that NumPy array into a standard typical Python list, something that does not have the fancy NP placed before it. Okay, our typical Python list. So that's that, a list array. Now this is the process of converting an ND array to a standard Python list. Now this is important. Lists cannot be broadcast by default, so we need to code a function to emulate what an ND array can do. Guys, do you remember, right, in the beginning of the first lesson in this tutorial series, we spoke about this little concept called broadcasting. And if you recall, broadcasting really had to do with that element to element operation, working with elements or working with arrays element by element, right? That's what broadcasting is. And for a fact, we spoke in that lesson, and I mentioned to you that lists one of the reasons why lists are slower than NumPy arrays is because of a process called broadcasting, which NumPy arrays support. Okay, and that is the reason why NumPy array is faster than your typical or standard array or list in Python. Now, given that fact, because a typical list does not support broadcasting, oftentimes you may ask yourself, right, how do I know that my NumPy array is faster than my typical or standard Python list? Now, in order to check speed, or in order to assume or confidently declare or decide which one is faster, what we do is a manual approach of comparison. Basically, we know for a fact, right, that lists by default they don't support element by element operations. But what we can do is we can create a function that will individually, affect each element in the list or the array. And by doing this, what we are doing is a manual broadcasting. Okay, so let's proceed to set up a function that's going to emulate the process of broadcasting, right, which by default an ND array supports. What we do here is define list times. So we're calling it list times because we aim to basically time the duration that a process takes to be performed on a standard Python list and then a NumPy array. So I also would like to mention that, this tutorial series of scientific and numeric computing in Python, really guys, you need to be on par with your, Python terminologies and your syntax and functions and so on, because I am not explaining that in detail. I am assuming that if you are watching this Scipy and NumPy tutorial, you are already familiar with the concept of modules, functions, and Python's basic syntax, right? Your looping structures and so on. It's nothing difficult. I do have tutorials on the channel, and yeah, I trust that you guys will be able to learn Python in 1 or 2 days with just the tutorials I have on the channel. So anyway, this function is taking in a list and it's taking in a scalar. Okay, now what we are doing within this function, for I and value in enumerate a list. So in case you didn't know, right, the enumerate function is a built-in Python function that helps us to iterate or cycle through elements in a sequence. Essentially what the enumerate function does is that it will take each element in the order in which they appear in the sequence, and it assigns each one a unique index. Okay, so numbers, regular numbers, it gives it in the form of 1, 2, 3, 4, and so on for each element in the order in which they appear. So that's what enumerate function does. Okay guys, now what I'd like for you to look at now, right, and understand is basically what we are doing. Return a list. We have created a function that's going to manually apply a simple mathematics procedure or process on each element in that list that we pass to the function. I told you broadcasting is where we affect each element individually. Lists can't do that. So we have now a function that can actually do that. And the reason why we're calling it list times is because we intend to time these operations just now. For now, I just want to make sure that you understand the simple function that we have defined. Okay guys, so what I'd like to just reinforce is that for the specific element that we are working with, we're taking the value and we are multiplying it by a scalar. A scalar, is just a random value that does not kind of change, or it's just think of it as a value, guys. So basically we are setting that element to be equal to the value multiplied by this common element that's going to be involved in the operations. So at the end of this loop we are returning the list to the main program. Now run this, compile your script, make sure your function gets compiled. So at the moment I ran the script and I know for a fact that in my interactive console I do have a function called list times, as you can see, a list with a scalar. Okay, so what I want us to do now, right, is basically, and remember, we still have that ARR, there's it here, ARR is still here. That was our NumPy array. Okay, now what I want us to do is as follows. Using Python's magic commands, I hope you guys are familiar with, the concept of magic commands and so on. Spider IDE is not the only IDE that supports this. Several other IDEs have their own equivalent of these special commands. But basically, Python's magic command known as time it will be allowing us to actually time an operation. Okay, there's a lot I can really speak about, guys, but the important point is you guys understand and you don't get confused. I want you to enjoy these lessons and sessions, and I want you to have maximum takeaways. But if you would like to know more, you can go Google on line magic and cell magic. Okay, line and cell, they're two different types, but the idea is the same. Anyway, coming back to the main point, what I'd like for us to do now is, using Python's time it magic command, I am going to time a specific line of code. Okay, specifically I'm going to time array. Remember, guys, array is that NumPy array, and notice that we have the ability to just take that array and multiply it by 1.1. 1.1 is that value that we just want to change all elements by. Okay, so if I hit enter, what's going to happen is my code will run and Python will time that for me. Okay, so I hit enter. I'm going to give it a few seconds or so, because at the end of the day I am working with 10 million elements. Okay, and as you can see, 54.8 milliseconds plus minus 4.13 milliseconds per loop, and it ran 10 loops. Okay, so let's do the same, but this time we are using list times. We are using, it's the same concept, we are applying element to element operations, but this time to a list, and we're using a function that was manually coded to apply those changes. So list times, and what we are doing is passing in our list array, which is not a NumPy array, so we are working with a standard NumPy array, and we're passing 1.1 as that value that's going to be propagated to each element. Okay, so again, when I hit enter, let's have a look at the difference in time. This should take relatively much longer. Okay, so hit enter. Okay, guys, and as you can see, right, drastically longer. Like if we are talking in the concept of computation, it took drastically longer. The reason why I say that is because the NumPy array was at least measured in milliseconds, right? 54. Whereas the standard Python list, mapping that change to each of the values manually, it took 1 second, guys. That's a huge difference, especially from a computational point of view. So I hope you guys finding this interesting, right? I really find this interesting. Anyway, that is the time it magic function. So you guys can play around with that, right? You have the ability to time a whole lot of other stuff in Python. So that's good. We have looked at a minor, well, kind of major difference between a standard Python array and a NumPy array. The factor lies in the speed. So as we just saw, moving on, guys. So what I'd like for us to do now is basically I want to introduce you to another method or function that's offered by the NumPy package. It's called zeros. Okay, zeros, and as you can see, there are a few parameters for the zeros function: shape, d-type, order, and so on. If you need assistance, what you can do is numpy zeros question mark hit enter, and it will pull for us the documentation for that specific function. So as you can see, return a new array of given shape and type filled with zeros. Shape is in the form of integers or tuple of integers. Okay, example, and they gave us an example. The d type, you don't have to stress about that. Order and so on. For now, I just want to introduce you to this function. It is an interesting one. So let's do, oh, I forgot to pass in a shape. Pass shape in the form of a tuple. Let's do 5 by 2. Okay, that's good. And now I want to print ARR. So I'll quit from that. The zeros function will the zeros function will generate for us a numpy array containing zeros that take the shape, or let's say in the shape of the given tuple. That's good. So if I hit enter now, I should be outputted with our the shape of the array. And I want you to pay careful attention, guys. The way in which you pass your parameters to, or your shape argument to the np zeros, it's in the form of a tuple, but there's two values in the tuple. The first represents the number of rows you would like in the array, and the second number represents the number of columns you would like in the array. And again, if I do, so let's do print arr.shape. Take a moment to, just soak this in, guys. This is information that's important. The numpy zeros takes a tuple for the shape parameter. Okay, the first value in that tuple is the number of rows, and the second value is the number of columns. And the shape method, when called on a numpy array, gives us a tuple as output in which two values reside, a first and second. The first represents the number of rows in the array we are working with, and the second represents the number of columns in the array that we are working with. So that's that. Now, the next thing I'd like to introduce you to is so let's just comment this. Okay, that's good. Now, the next thing I'd like to tell you about, guys, is, I'll do this in the console itself. So we'll do arr dot, and I want to show you ndim. So this is kind of like a spoiler, right? I'm pretty sure you see all of the methods that can be used on this numpy array object. I want to just enlighten you or show you the ndim method, right? If I hit enter, you'll see that the ndim method basically tells us the number of dimensions that we are working with in this array. Right? For now, there's not much I want to speak about this method. I just want to introduce this method to you. It's important you know this exists, especially if you are taking on machine learning and AI topics in the future with Python. It's good to know that this method exists, because to be honest with you, it is used kind of a lot, especially when it comes to checking the number of dimensions we have in the target vector or the features matrix. Okay, so that's that. With that, guys, we've actually made quite a bit of progress. We may be moving at a slow pace, but this is the pace at which I like to take my stuff, understanding it properly from the beginning. Okay, so I hope you guys are finding this interesting. This was part 2 of our scientific and numeric computing tutorial series in Python, and this video is actually clocking 31 minutes. So I think with that I will end the video here, guys. Thanks for watching. Thanks for staying till the end of the video. I hope you are finding this interesting. Leave a comment down below if you'd like for me to, change anything or add 1 or 2 more things. And with that, guys, thanks for your time. Good luck with your work, and I'll see you in the next YouTube video.